How's that?
Yep, perfect. Thanks to
Okay.
the delay, we are about 53 people now, so it's a half century.
You can always count on technical delays for
Yeah,
sharing screens.
cool. I'll give a short introduction to Ben.
Okay.
Yeah, Ben is a close friend of mine. It's like we go, I think, from 2018. Have known Ben. We started working in at my first company, Abridge, and even before that, Ben did a PhD in neuroscience. He also it's like a multilingual. He knows like five, six languages. He worked on like merging neuroscience with machine learning in China. Did a lot of work on that side. And at Abridge, we worked together on Gen AI before Gen AI was even a term, right? And then more recently, Ben is working in Swoop on uh, agentic uh, infrastructure for the last 2 years. So Ben has a lot of knowledge on agent building, which I'm starting to do now. So not in the same field, so we are not competing. So I'm also excited to learn more about this field. Awesome. Yeah. Get started, Ben.
Okay, cool. First of all, thank you for inviting me. Sai, you go by Sai here. Is that the
Yeah,
name of?
Sai.
Okay. Sai famously has switched names many times between his first and middle name, so I never know what to call him. Um, yeah, so I'll do a quick, I guess, or a little bit longer intro of my background. So I got into AI in kind of a less traditional route. I went to school originally for psychology and mathematics. And then I got a PhD in cognitive psychology. And when I was doing my PhD, we were doing neuroimaging research. So we were using functional magnetic resonance imaging to take pictures of brain activity. And we were focusing particularly on bilingualism and how bilinguals represent information in the brain, particularly words and what words mean. And at the time, word embedding models were kind of taking off. So I don't know how far back some of you may or may not remember, but this would have been around the time that Google released Word to Vec, and then went right up to around the time Elmo was released and some of the first Transformer models, BERT. And that's when I joined a bridge and met Sai. This was 2018. I finished my PhD in 2020, but had left early to join a startup and have been in the space ever since. I've always been in healthcare, and I started out working on sort of natural language understanding in doctor-patient conversations, which is what Sai and I did at a bridge. This was before ChatGPT, about three-ish years before ChatGPT, or the big ChatGPT, GPT-3 came out. So we were still kind of like training models a lot back then and doing a lot of classic ML neural network kind of stuff. But then I did a little stint working in a cancer related space and then came back to a bridge. And this was right when ChatGPT 3 came out and we ripped all of our old work out because nobody uses that stuff anymore. And started getting more into kind of prompt engineering kind of work. And then I came to Swoop, and for the last 2 years, what we do is we actually build a platform that lets our workers make their own agents. So we have a very sort of agnostic platform. We don't build agents necessarily for specific use cases, which is what a lot of companies do. They try to solve specific problems. But instead, we have a platform that allows people to make their own agents. And So you can come in and design an agent to do whatever you want it to do to automate your work. And so a lot of what I'm going to talk about today is actually everything I'm going to talk about is stuff that I actively worked on in the past 2 years and continue to work on every day. We have a lot of snapshots of some of our code and some of our infrastructure, so you can kind of see how this is really actually done. And I think I was talking to Prabhakar. We'll probably stop about halfway through for questions, but feel free to ask questions as we go. I may not be keeping a close eye on the chat, so feel free to speak up, or Prabhakar, you can interrupt me if there are any questions. Sound good? Cool. Okay. So we are going to start talking about just what is an agent. I saw a little bit of some of the talks and boot camp that you all have already done, so I think most of you are familiar at least with how LLMs work. I hope that's true because I'm not going to go into a lot of detail about that. But there's basically a pretty simple progression of this concept of an LLM to what people refer to as an agent. And I'm going to introduce an intermediary concept, which is a chain. And chain is the same idea that the famous library lang chain is built around, but it's the idea that you kind of have a process in which an LLM is just one part, right? So one chain, a classic chain might be, okay, a user sends a query, and then you do RAG to pull in any relevant documents related to the user's query. You construct some prompt out of the documents in the query. You pass that to the LLM, and then the LLM responds. So that's a pretty simple chain, right? You have input, you have the RAG portion, and then you have the LLM. And we call it a chain because there's really no looping and there's no sort of conditional edges. It's kind of just a straight linear chain. The difference between that and an agent is really just usually some sort of loop. And it's usually related to some sort of cognitive architecture. And we're going to talk about these in the next slide. But yes, so the main difference here is that usually the agent will keep running based off of some condition for an unknown amount of time once you sort of start the loop. So the agent has some sense of autonomy in actually deciding how the loop gets executed and for how long the process is going to take. Let's see. So just a quick anatomy of AI agents. They usually consist of a few different things. Usually there's some LLM. We provide access to a lot of the major LLMs. So Claude, GPT, Google Gemini. We let our users switch between them because some LLMs are better for different tasks, and it's kind of hard to know ahead of time. So we just let our users toggle between them if they want to. Then there's usually some set of instructions. A lot of times it's like what you want the LLM to do, right? It would be like, could be as easy as answer the user's query to something more complicated. We also work with personas. So this is often where you would include personality type stuff. Like you might say, hey, you are a middle-aged mom who lives in the suburbs of San Francisco, and you are Latina, and you think about the world in this way, and you should respond in a way that is consistent with that personality. Um, these types of use cases often are used in like advertising. If you want to like target a specific kind of group of people, a lot of times they'll make personas and then talk to these personas and present ads and ideas to them as if they were real people. Um, and then most organizations have some proprietary data that need to be accessed, right? So whether it's in a database or it's just a bunch of files in Google Drive or whatever. There's usually a data component, and then there's an underlying architecture for how the agent actually works. This talk is mostly going to focus on architecture, but I can answer questions about other parts if people have them. So we're mostly going to focus on single agent architectures. Once you get these, some of the multi-agent stuff is, I think, a little easier to understand. And I do have a couple slides on multi-agent as well. So this is probably the most common architecture, and it's called a React agent. And it's fairly simple. And this agent actually, I will say, has a pre-made implementation in LangGraph. So LangGraph is another library offered by LangChain that basically implements agent architectures in a graph. And for anyone who is interested in this, I highly recommend that you look at LangGraph instead of LangChain libraries, because there's actually an implementation of this React agent in both. But I think the LangGraph one is superior, and it's a better framework if you actually want to build AI agents. Um, you can basically introduce few simple concepts to understand how LangGraph works. There are basically nodes and edges and conditional edges. So a node is typically some function, um, and that you code on your side, and the edges determine where the output of those nodes go. And sometimes there's a conditional edge, so it could go to two different places. So then you have to write another function here that decides when to or where to go. And so a React agent basically works by um, sending a question or an input or a prompt to an LLM. And typically this LLM has tools. So maybe it has the ability to crawl a website, maybe it has a calculator, maybe it has a database connector so it can read data from a database, anything like that. And basically this part calls an LLM that has tool calling. Not all LLMs can do tool calling, although that's increasingly rare. But it is true that's not you. Some of them do not, especially some of the older ones. Um, and it makes a decision. It either answers the query or it calls a tool. And if it calls a tool, it then observes the output of that tool and makes another call to the LLM. And basically, this, as long as the agent keeps calling tools, it will stay in this loop. So you can imagine if you have a task like, oh, I want you to analyze this Excel sheet and produce a bunch of graphs. And maybe you have a code interpreter like tool where the LLM can actually write and execute code. A lot of times this results in a lot of tool calls because usually the LLM will make some sort of coding mistake. It will get an error. It updates the code. It gets another error, kind of like when humans write code. And so, maybe first it just cleans the data, and then it does the analysis, and then it makes some graphs. So it could be, 10, 12 total tool calls before it actually responds to the user. Um, and I'm going to pull a little bit more on tool calling next. But on the right here, this is a trace of from our actual system of a React graph execution. So basically, you can see from the input, we do some formatting and trimming if necessary to keep the messages inside the context window. And then we go to the assistant, which has its own graph. So that's an assistant subgraph. And it starts by generating. So it just starts by thinking, basically. This node, sorry, is an LLM call. You can see we called GPT-4. And it decided to use a tool. And we have a tool that basically does RAG. called a document retrieval tool. So it called the document retrieval tool because it wanted to look at some documents. Okay, so that it got output from the tool, and then it called the tool again, right? This is pretty common. Um, so this is basically what it looks like, and it just keeps calling tools until it decides to answer the question. Tool calling is pretty interesting. It's where we spend a lot of our work because this is all the tool calling happens on our servers, whereas the LLM usually executes on a different server on OpenAI server or wherever, unless you're self-hosting. So there's a couple things to understand. One is how do LLMs know about tools? So I have an example up here of a web crawler tool. This is also all of these traces, by the way, are from Lang Smith. This is a production environment. It's not open source, so this is enterprises basically pay for Lang Smith to do logging and tracing of their systems. Um, so it just kind of makes some nice graphical pictures of like what's going on. But basically, this is an example of how the LLM sees the tool. It has a short little description, right? It says, okay, you can use this tool to scrape or crawl a website. And this describes the required input to the tool. So you'll see it has two parameters. One is crawl, which is a Boolean, and defaults to false. If it's true, then it will actually crawl, which means it will keep following links deeper and deeper into the website. Otherwise, it just scrapes the page. And then it takes a URL, which is a string. And when LLMs call tools, they basically say, okay, I want to call this tool by name, so the web crawler tool, and then they input any necessary parameters. So here's an actual tool call from our document retrieval tool. I grayed out some of the information because it had some unique database info, but basically we give two options. One is a query. So this is an LLM generated query. And then we also allow it to filter based on file IDs. So, maybe the LLM only wants to look at contents of a certain file. So this is what this does. Basically, it passes this name in and these parameters. And then we take that information, we do RAG and put it through a Python function, collect the outputs, and then pass it back to the LLM. So each tool call actually has a unique ID, and this helps track the inputs and outputs because they actually happen in separate LLM calls. Um, so one thing to think about that I think is interesting is code boundaries. So where do we actually write code? Where do we actually operate on a day-to-day basis? This is just an example of our system. It may not be every system. We actually have a front end that collects user input. So it's an app. I'll show you some snapshots from the app a little later, but it's actually separate from our agent platform, which is mostly where I work. This app is written in Ruby, and the app that I mostly work on is written in Python, and we use LangChain, LangGraph specifically. And we also use Llama Index for RAG. So I don't actually have to deal with the sort of UX problems of collecting user input and all of that stuff on a day-to-day basis. I usually just get some sort of JSON from the front end, and that's where I start. And then, usually the first step in any agent flow is thinking or generation. So basically, we construct a prompt and send it to the LLM. And that doesn't happen on our server. So usually there's some sort of async processing here where we are doing other things while the LLM is thinking, and then we're streaming tokens as they're coming in. Once the LLM sends a message back, if it doesn't have a tool call, we format it as a response, and then we send it back to the front end. If it has a tool call, then we have to unwrap the parameters, validate them, and put them through a Python function. And a lot of these tools actually call out to external services as well, right? So we have tools that call out to Databricks. We have tools that call out to Llama Cloud. We have tools that call out. So then again, here is another point where a lot of times there's a code boundary where actually you're sending requests to other servers and just kind of waiting. Um, so that is code boundaries. And then there's one more architecture I'm going to talk about that we use for single agent called plan and execute. This is pretty different from React. React is a very kind of open-ended architecture. Um, it's good for just kind of generic use cases that you don't really know what the user is going to want. But if you have a task that's kind of complicated, like data analysis or something, this type of architecture is typically better. And what happens in a plan and execute agent is that, let me just check time. Okay. I think after single agent architecture, we can take a little break, Sai, and then cool.
Yeah,
So
that works.
basically, the first, like, I send a message saying, hey, we are going to analyze this data, right? And so the first thing that the LLM does is it makes a plan. And it says, okay, I'm going to make a plan that has 6 steps for how we're going to analyze this data, right? First, we're going to inspect the data. Second, we're going to clean the data. Third, we're going to do the analysis. Fourth, we're going to make graphs, whatever, right? Okay, so once it makes the plan, it goes to this next step, which this step basically does 2 things. One, it pops the highest step off the plan, so the first step in the plan. And then it passes that step to a React graph, like here, to actually do the task. And then once that task is done, it passes the output back to the planning stage, at which point the LLM has the option to update the plan. So it may find out during data inspection that, oh, something wasn't how it thought it was going to be. So then it can update the plan. And then it goes back right here and says, okay, now we pop the next step off the plan, we do it, we send it back. We replan if we want to. And this keeps going on basically until the plan is empty, or basically, you've popped the last item off the plan, there's nothing left. And then you finally respond. So it creates quite a bit more structure for how long the LLM will run. I will say these typically run quite a bit longer, but they work better for tasks that require kind of detailed um, step-by-step thinking, like data analysis or something like that. And I'm actually going to show you how one of those looks in our system. So I said, do research on associationist accounts of human reasoning. It's a topic I've kind of been interested in lately as I kind of start thinking more and more about LLMs doing things like reasoning and planning. Um, and so this is actually just the final response it gave me. So I was talking about plan and execute. Sorry. Here is an example of the output of the end of a plan and execute chain. We actually hide most of the thinking in this little chip up here. So I'll show you what that looks like with the thought process expanded. So here you can actually see the initial output of the plan. Um, and it tried to execute the plan the first time. And it was like, oh, I can't open a web browser, which was kind of a weird thought, but I don't know. LLMs are weird. It does have a web crawler tool. So it went right back to the replan, and it redid the plan and changed it to use a search engine. And I guess that was enough to get it to actually use the web crawler tool. So it searched Google um, for the association account. You can start to see the output. So this is actually what the inside of the thinking process looks like. Um, to our users. So we expose all of this to our users so they can see how the LLM was thinking so that they can debug and troubleshoot when they do things that are wrong. Um, so that is my those are the two main architectures that we use that are single agent. We also do reflection, but that's a relatively simple architecture. I think they talk about it in the paper that I sent. You, you can look it up, or we can talk about it later. At this point, I think I'm going to open up to questions. I know there are probably some in the chat that we lost. I don't know if people want to repost them.
Yeah, I remember one question was about
Yeah.
not related to agents, but one
Hmm.
was about how can we make LLMs work in some of the low resource languages? Uh,
Hmm.
like, I
Yeah,
mean, world has a lot more languages than just English and maybe French or Spanish.
totally.
So
There's a huge bias against non-Latin scripts, and there's a huge bias against just in available data, right, for a lot of languages on the internet. Because most of these models are trained on data from the internet. So if a language is not represented on the internet, it's probably the LLMs are going to be not as good. And then you also have to think about more and more large companies are employing these oh God, like human feedback techniques to do reinforcement learning. And so that requires extra effort, extra money, human labor. And so you can be sure that that's only happening for the biggest sort of languages like Chinese and English and probably French, because France actually has quite a few companies in the AI space. But yeah, basically, as you go down the list, these sorts of architectures are going to work less and less well, right? If you're working with a lower resource language, you may not even have access to an LLM that's been trained on tool calling, you which is kind of essential for agent architecture. Um, I would say your best bet in that scenario would be to try to translate the parts of the outputs to a more powerful LLM in one of the bigger languages. So you might have to figure out how to create a translation layer to do tool calling from, if you are dealing with a language that doesn't have built-in LLMs that do tool calling. Similarly with reasoning, we actually started out by offering reasoning as a tool. So basically, the LLM would call another LLM that would think really hard, right? And then pass it back to the calling LLM. So there are ways to get around this, but generally speaking, it's going to require some, I think, intermediate layers. And I think translating that stuff is probably going to be a little bit like whack-a-mole, in the sense that like you're not going to really know what all the problems are ahead of time, so you're kind of have to build it and then see what happens and then fix it and stuff like that.
yeah, that makes sense.
Are there any other questions?
No, I think you also have a hard stop at 2. So let's proceed
Okay,
further, and then I
cool.
can answer questions at the end. Yeah.
Yeah, so multi-agent architectures, basically now we're just talking about architectures where there's more than one agent. The paper that I sent out kind of nicely summarizes, at least conceptually, into two kinds of multi-agent architectures. In reality, this is more of a spectrum than, like there's only two kinds. But basically, you have one type that is very top-down, right? And usually this looks like a delegation or a router architecture, it's often called. And so often, like the router or the manager will create a plan or something and then give tasks to other agents. So you can imagine that the one on the top of the triangle would be the manager or the router, and then the ones below that are maybe workers that do things. Maybe you have a data analyst, maybe you have a creative writer, right? And so depending on the task, you would delegate different tasks, sort of how companies work. And you can also recur this architecture, right? So you can have a manager hand off to a lower level manager who then hands off to, even lower. Um, On the other side, you have more horizontal architectures where kind of everyone's connected to everyone. We use an architecture like this to simulate focus groups. So basically like this, like brainstorming sessions, right? Where we might want to generate different personalities, and then each personality can sort of chime in almost at any time. And usually there's only one human involved, but there may be, three or four different personas who you're brainstorming with. And so then they can kind of, one AI agent can say something, and then another AI agent can react to that, and you kind of get more varied ideas. It's particularly useful when you want LLMs to give you more kinds of different ideas. And one of the nice things about personas is that LLMs have this very generic robotic way of responding sometimes. And a lot of times, if you ask them the same question the same way, you're going to get a very similar answer. So you can't just send the same question to the LLM six different times and expect to get varied answers. This is where persona generation kind of helps, because you can actually give the LLM information about, okay, I want you to respond like a professor. I want you to respond like a CEO. I want you to respond like an investor, right? And then when you kind of prompt them that way, you start to get the kind of variation and ideas that you're looking for. Um, so I'm going to talk about one uh, concept in particular. And this was introduced by OpenAI's Swarm architecture, which is an open source GitHub architecture. So if you're interested, you can look at it. But the idea is called Handoff. And we actually implement it as a tool. So this is a snapshot of our actual code. So I can talk about a few things here that are kind of interesting for people who may be a little closer to the code and are interested in how people actually do this. Um, but basically, it's a tool, and it's a pretty simple tool in some regards, right? Basically, we tell the LLM, you have these other people that you can hand off to. And when you hand off to them, we basically copy the conversation plus any message that you want to send. And then the control flow. So this is where things get complicated. The control flow now changes, right? Because now we exit one agent's loop and go into a new agent's loop. And this can be complicated, especially if you have agents with different architectures, because sometimes the architectures don't line up well. Like if you go from a plan and execute architecture to a React architecture, React architectures don't handle plans the same way that plan and execute agents do. So then you can start to get like unexpected behaviors if you don't put up guardrails. But aside from that, basically it's just a tool call. And the LLM just says who they want to hand off to, which we have a unique ID for every assistant. And then optionally it can provide a message to, give additional instructions on why it handed off and what it wants it to do. So it's pretty simple. You'll notice some interesting things going on here. So we use Pydantic to define all of our schemas. This is very common in industry. It kind of helps with data validation and also turning all of your tools, which are Python objects, into JSONs and messages that the LLMs can understand. So it just kind of helps with a lot of the sort of glue code of translating things back and forth from JSON to database to whatever. Um, and so this in JSON structure basically just looks like a little dictionary with two keys. One key is a UUID and one key is a string. That's a message. Sorry. Let me go back. Uh, and then the handoff tool, the way that's implemented requires a little bit more understanding of how LangGraph actually works. So I'm not going to go too deep into the details there, but basically it just, like I said, it switches the control flow. What's interesting about this pretty basic concept is now you can really implement kind of any architecture you want via handoff by just constraining which assistants can hand off to who. right? So if I wanted to create a vertical architecture, I can create a manager who can hand off to sub managers, and I can create sub managers who can hand off to worker bees, right? And in that way, we enable our users to create their own multi-agent architectures kind of however they want, and they can make the rules themselves. So we don't have to try to predefine or guess what kind of multi-agent architectures our users are going to want because we don't know. So handoff is a very powerful idea that actually enables all sorts of multi-agent architectures. We are designing another one that's a little less free-flowing. So the bad thing about handoff is that it's voluntary. So basically the LLM, because it's a tool call, can choose to do it or not. Sometimes you have a pipeline that you want, okay, I want this agent to do something and then pass it to this agent, more like a conveyor belt. We're designing a system that also does that, but it's a little more beta at the moment. Um, okay, so a couple other topics. So one thing to be aware of is that increasingly a lot of LLMs are reasoning and planning not in the agent architectures that you build, right? Like I showed you earlier, but even already on the server, the provider server. So OpenAI's agents are actually already doing reasoning loops and planning loops before they even come to you, and then we're wrapping them in even more reasoning and planning loops. So the amount of computation is kind of exploding, and there's a little bit of duplication of what's going on. Um, so this is kind of something to watch, whether the degree to which this needs to be implemented by you versus will be taken care of for you by, say, an LLM provider may change over, the next 6 to 12 months. So the architectures that we're using today will very likely change around these two particular aspects. Um, but basically, the benefits of reasoning and planning are just kind of you're more likely to get a right answer for a complicated task. And I think this has really been studied a lot in like mathematics. If you look at how LLMs solve complicated math problems, these sort of chain of thought processes work better than just the LLM just trying to answer, you know, um, in kind of a zero shot manner where it just basically tries to give you the answer. When it does that, it's much more likely to fall into some of the pitfalls of LLM association problems. I don't know how many of you have seen like the famous how many R's does the word strawberry have? But it's like a really simple task that LLMs failed on even until months ago, and a lot of LLMs still fail to correctly answer how many R's the word strawberry has. So these sorts of thinking processes were really designed to fix those sort of problems, but they have pretty broad use cases. Um, I'm going to talk a little bit about some of the challenges that oh, that's already two. Well, I can stay over just a little. So a lot of the problems that we actually have in our system can be boiled down to, four-ish different things. One is context window sizes. So all kinds of LLMs have different context windows. They can accept different amounts of information. This becomes really complicated in a multi-agent architecture, right? Because you could be starting with Gemini, which has some of the biggest context windows in the industry. It can take like 2 million tokens. And then you can pass it off to a different LLM that has a really small context window. This is a very common way that context gets blown up, and then you basically get an overflow error from the API of the LLM provider. Another place where this happens is tools and large files. A lot of people want to analyze these 1,000-page PDFs, or they pull a database query, right, that returns 10 million rows of data. Not going to work. So these are the kind, this is, we spent a lot of time engineering around these problems and trying to find ways to handle them, both, through prompting and also the way we design our tools and the way we design our architectures. Another problem that we have is long running processes. So you start to see this with certain kinds of tools and multi-agent architectures. but it's not a good user experience when basically I tell an agent, okay, I want you to do some data analysis, and then it goes off and runs for an hour. You have no idea what it's doing. You don't even know if it's working, and an hour later, best case scenario is you get something you didn't want. Worst case scenario, medium case scenario, you get an error message that you can actually read. And worst case scenario is you just never get anything at all, right? And you don't know why. This so a lot of is more of a software engineering problem, and a UX problem, but it causes a lot of issues around, okay, now we have to stream certain information to our users. There's a really interesting concept that I haven't brought up here that's probably worth looking into, which is interrupting uh, graphs as they're executing. So you can actually um, create a tool, say, that stops the graph, exits the whole control flow process, and requires your user to input something. It's called like human in the loop, basically, right? So like maybe the LLM needs some information from the user to go on. So now you have to be able to serialize the whole graph state and then rehydrate it when you get the user input. This is another common sort of pattern it's more of a software engineering pattern than an ML topic, really. Um, but these are the kinds of things that a lot of enterprise production scale systems are dealing with. One really annoying thing that we deal with all the time is just non-standard data format. We're constantly translating message strings from OpenAI to LangChain to our data, back to LangChain to Google Gemini, back to ours, and they're constantly changing. And then Google releases the model that thinks, and the way they store their thinking data is different from the way that Claude stores their thinking data. So then every single provider has to have their own special like string translation. That's probably just like the most tedious, annoying part that we deal with. And then a lot of complexity. Most users don't really understand how this stuff works. So how do you make a tool that they can actually use that's not overly complex, right? You don't want them to sit there and design a whole agent graph. That doesn't necessarily make sense to them. So kind of boiling everything down to the right concepts, getting the right sort of levels of abstraction on the front end is another problem that we deal with a lot. Okay. I can do probably maybe 4 or 5 minutes of questions, and then I'm gonna have to jump.
One question that came in, Ben, was you
Hmm.
mentioned that the LLM providers may implement their own reasoning step, and we might have our own reasoning step, and that might
Yes.
make it more complex. Is there any negative effects to that? Or is it just like, okay, we are wasting
Yeah.
token?
Right. I mean, one, you're wasting tokens and time. I would say time is more of an issue, right? Because the user often doesn't want to wait. And so the longer that the wheels are spinning and they don't really know what's going on, and then they get back this massive wall of text and it's like largely repeating itself. So it's a pretty big UX problem. Um, from the point of view of actually, solving problems, I will say less is more. I think the longer that LLMs generate text, the more likely they are to do something weird. So you really don't want to add any steps that don't need to be in there. That is generally a sort of something that we have found to be true. The more you can break tasks into small pieces and the less that they generate, the better.
Got it. Yeah, I read I mean, there are a lot of papers where if you increase the thinking budget, it even gets a simple question wrong as well. Um, that makes sense. And I mean, I think the UX problem you mentioned, it's probably more related to cases where you are showing the thinking step as well. Uh, Maybe there are some cases where you don't show the thinking stuff, right? You just show the like final output of your agent
Yeah,
architecture.
totally. There are cases where you might want to hide that, right? Maybe some of the thinking steps access proprietary data, and you don't
Yeah,
want to
yeah.
reveal that to the user, right? Um, so yeah, there's a lot of questions around what to reveal, what not to reveal, how much information does the user need. Um, our tools are largely internal, so we show our users almost everything because it helps them fix problems, right? Like if they can see what the LLM was thinking and where it made a mistake, then they can tell it how to fix it. We do have some client-facing agents, and we show a lot less in those cases because we often don't want to show our database queries and we don't want to show too much detail about what's going on.
Can you talk about the use case for which you're building agents in your company?
Yeah, we do all kinds of stuff. So the internal use case is just productivity. That's why we have this platform to basically build your own agent.
Productivity for like your customer service agents or like who?
All kinds of people. So yeah, for our customer service agents, for our legal people, legal is very textual, right? Legal has to review so many documents and they have to find tiny snippets of text that they have to quote and cite all the time. They love stuff like this. People making presentations, people use it to proofread their emails. People use it to make documents for the CEO. They'd be like, okay, or maybe there's a conference and somebody will give an LLM a web crawler and say, hey, crawl the conference website and tell me about all the most interesting, you know, posters about this one topic, right? Because they don't want to read it or they don't want to sit there and click through the entire website. A lot of stuff like that, people are automating internally. Externally, we mostly work in pharma. So we are building agents that automate stuff for pharma, which um, in some cases is related to advertising. We do persona agents for various. So if you have a rare disease, like some kind of cancer, we have data that can break down different kinds of people in that. Maybe one person is a elderly woman who watches, this one show on Netflix, and then another one is like an older man, and maybe he reads the New York Times, and so we get all these kind of like different personas in, and then they can kind of figure out how to market drugs to these people. But there's a lot of complicated. So the company that I work at specializes in marketing in the healthcare industry in the US, which is highly regulated and has all of this like statistical stuff that has to go on to make sure that patients cannot be identified. So we sell data to pharma companies, but we don't tell the pharma companies about the patients specifically, and we add a bunch of noise to the data so that they don't know who's who. And so then the whole process is fairly complicated, but it kind of boils down to the persona stuff is one of the agents. We also are building an operating system for our sales folks that is agent-driven UI that lets them kind of access and get insights from different data silos in the company, right? A lot of companies have kind of grown and acquired companies over their lifespan, and they had just have data in so many different places, and most people only know how to access like one or two of those. So it's like a huge organizational problem for people to be able to get all the
Got
information
it.
that they need in a timely way. Yeah.
Got it. Ben, one more question.
Yeah.
There are more
Yeah. Yeah.
questions in the Q&A, but one question I think you are best to answer is, uh, what is the role of classical machine learning in the current landscape
Uh,
dominated by AI, agents and RAG systems?
the main role, in my opinion, is understanding how LLMs actually work as a transformer and kind of if you have a line of sight on the types of problems that LLMs used to have, like before ChatGPT, I think you have a pretty deep understanding of the types of things that transformers are good at and bad at. It's really like troubleshooting and prompt engineering. And then, another thing I didn't talk about is like evals. traditional software engineers are not really good at evaluating stochastic systems, systems that don't behave deterministically, you know? You can't really use unit tests to evaluate these types of systems. So that's another place where I think classical ML comes in because you still rely on those skills to evaluate and score your systems and how to decide, you know, when to update and when to improve them and stuff like that. But the actual
Got
model
it.
training, I don't do that. I think more and more that's going to be, you know, a few companies, mostly large companies, that are going to sort of dominate the LLM, actual LLM training.
Yep. How much time do you have?
Um, one more. Okay, then
Okay.
I really gotta go.
I think this is like maybe if okay, I'll just read it. In a React-based AI agent, if you could
Hmm. Hmm.
eliminate all latency in either
Hmm.
the reasoning module or acting module, which one would you choose to ensure uh, the performance doesn't degrade in
Right.
real-time environments like autonomous driving?
Mm, that's interesting. So what? So you're saying if I could
Reduce
totally,
the time taken in reasoning module or acting module, which one would you do?
but there's
In
no degradation in performance,
yeah,
or there
applied
could be.
to there could be, but it's the
Okay.
application is
Like where would
autonomous
you
driving or
focus?
real-time environment.
Yeah. Yeah.
This requires more
I
thinking, I
mean,
understand.
yeah, I mean that's hard to say because in that sort of environment, you know, the error compounds between them, right? Like if you need to turn the wheel and that's a tool, you have to do that in a certain amount of time. And if you have to reason through whether you need to turn the wheel, uh, then then I don't know, right? Like which one would you choose? Um, I mean, ultimately you have to turn the wheel, right? Maybe you don't have to reason and maybe you'll make the right choice anyway. So probably I would say in that type of system, you're going to want really fast feedback signals for actions, right? Like if the if you turn the wheel, you want it to happen immediately and you want to start getting feedback right away, right? Because you need really fast relay systems between in your sensors and your outputs. Um, the reasoning you're probably going to want to decouple in some way so that you can still act, right? Sort of asynchronously while you're thinking. That would be tricky.
Awesome. I'll let you go now, and yeah, we will have like a couple of questions and then close it out.
Awesome. Well, thank you for the invite, and
Yeah.
I'm
Thank you,
sorry
Benjamin.
that we all had to experience that hack. And I hope you all have a good day. And I will send the
Thank you,
slides
Benjamin.
to Sai, and he can share them more broadly.
Awesome.
Thank you, Benjamin.
Thanks, Ben.
Okay.
Bye.
Yeah.
Thank you all.
Bye.
Bye bye.